Hello and welcome to the AI Research Roundup. I am your host, Alex. Today we're looking at a paper called ProRL, Prolonged Reinforcement Learning Expands Reasoning Boundaries in Large Language Models. It tackles a big debate. Does reinforcement learning, a training method that uses rewards to guide a model, actually teach it new reasoning skills? Or does it just amplify what the model already knows? The authors find that prolonged training can help models discover completely new strategies. They introduce their method, ProRL, which uses KL divergence control to keep the model stable during this long learning process. And for those of you who want to try out these methods, the team has released the code for this work in a repository called Reasoning Gym. It's a Python library specifically designed to procedurally generate, or create on the fly, new reasoning tasks for the model. This allows for that prolonged training we talked about. The repo includes the core library and all the scripts to replicate their findings. It's a great resource if you want to dig into the details yourself. Alright, so this first figure really visualizes the benefits of this ProRL approach. On the left, you can see performance climbing over thousands of training steps. The two lines show pass at 1 and pass at 16. These are success metrics. Pass at 1 is the score for the model's first attempt, while pass at 16 checks if any of 16 attempts are correct. Both are clearly trending up. The middle chart shows the creativity index, which measures how novel the model's solutions are, and we see it increases significantly. Finally, the radar chart on the right shows massive gains across all task types compared to the base model. So we saw those impressive performance gains, but what does the training itself look like behind the scenes? This chart shows us exactly that, plotting two key metrics over thousands of training steps. The purple line shows entropy, which is a measure of randomness in the model's predictions. You can see it drops quickly and then stays low and stable, a key goal of the ProRL method. At the same time, the orange line, which is the response length, steadily climbs. This suggests the model is learning to generate longer, more detailed reasoning to arrive at its answers. Okay, so we've seen that the training process is stable, but what about the results? This first table gives us a detailed look at performance on math problems. It's measuring the pass at 1 score, which, as a reminder, is how often the model gets the right answer on its very first try. The model trained with ProRL is on the bottom row, and as you can see, it consistently outperforms its base model and even a math-specialized model. In fact, its scores are nearly on par with a much larger 7 billion parameter model, which is really impressive. And we see a very similar story for coding tasks. This table breaks down the pass at 1 scores across a bunch of different coding benchmarks. Again, the ProRL model is on the bottom row. It not only crushes its base model, but also outperforms a specialized deep coder model by over 6% on average. What's more, on benchmarks like Codeforces, it even surpasses the much larger 7 billion parameter model. This shows that the gains from ProRL aren't just limited to one domain. The method helps create a more versatile and capable model all around. And that versatility we just talked about, it really shines through in this next table. Here, we're looking at performance on STEM problems, instruction following, and logic puzzles. The results are, well, pretty dramatic. For the logic puzzles from Reasoning Gym, the score jumps from a mere 4% for the base model to over 59% for the ProRL model. But the most compelling part is on the right, which shows results for out-of-distribution tasks. These are problems the model has never seen before. On the BoxNet task, the base model scored 0, but the ProRL model solves it. So we saw ProRL can help a model solve problems it previously failed on completely, which leads to a key question. When is it most effective? This figure provides a clear answer. The scatter plot on the left shows a strong negative correlation. Basically, the worse the base model's initial performance was on a task, the more it improved after training. For tasks it was already decent at in what the paper calls the diminished area, the gains were minimal. This suggests ProRL is most powerful for expanding a model's reasoning into new territory, not just refining existing skills. And these next graphs really visualize those different improvement patterns. Each plot shows the pass at K-score, which is the chance the model finds a correct solution within K tries. The blue line is the base model, and the green is the final model after ProRL training. In the top row, the diminished category, you can see the base model was already pretty competent. The final model is a bit better, but the gains are small. Then in the middle, we have the plateau tasks, where the model gets a good boost early in training, but the performance quickly levels off. But the most exciting part is the bottom row, the sustained improvement tasks. On problems like DICE, the base model scores 0, but the final model climbs to nearly 100%. This is clear evidence that prolonged training is uncovering genuinely new reasoning abilities. What's the big picture here? The ProRL paper shows that with prolonged, focused training, we can push LLMs far beyond their initial reasoning capabilities. It's not just about getting slightly better at things they already know. It's about unlocking entirely new problem-solving skills. This suggests the limits of current models might be more about our training methods than the architectures themselves. A really fascinating insight. That's all the time we have for this week's AI Research Roundup. Thanks for tuning in, and I'll see you next time.